Science and Technology will come to order. Without objection, the chair is authorized to declare recesses of the committee at any time. Good morning. Everyone's here. Welcome to today's hearing entitled Composite Materials Strengthening Infrastructure Development. I recognize myself for 5 minutes for an opening statement. The purpose of this morning's hearing is to review a NIST report on overcoming barriers to the adoption of composites in sustainable infrastructure and discuss the value of developing composite standards for infrastructure applications. While not widely adopted yet, composites have been used in select construction projects across the country. As we will hear from our experts today, fiber-reinforced polymer composites produced in the United States offer durable, sustainable, and cost-effective solutions in a variety of infrastructure applications as diverse as dams, levees, highways, bridges, tunnels, railroads, harbors, utility poles, and buildings. However, without proper design guidelines and data tables to harmonize standards and create a uniform guidance, the practical use of composites to build durable and cost-effective infrastructure will continue to lag. National Institute of Standards and Technology is well poised to lead research to provide evidence and data needed to set industry standards and design guidelines. NIST has a deep and varied expertise in advanced composites, which I look forward to hearing more about in the hearing. It is my understanding that there are over a dozen projects across NIST that work to measure, model, and predict the performance of advanced composites for a variety of applications. I'm well aware of the challenges our nation's infrastructure is facing and the anticipated cost of its restoration. I look forward to learning more about the potential value of using composites in infrastructure and the economic case for composites as an alternative or supplement to conventional materials in infrastructure projects. I appreciate you all for taking the time to join me for this hearing as the administration and Congress begin to consider how to tackle the nation's infrastructure challenges. It is important to understand what role composites can play. I now recognize the ranking member from Illinois, Mr. Lipinski, for opening statement.
Thank you. I want to thank Chairwoman Comstock in her absence today for holding the hearing on this important topic. And I want to thank the witnesses for being here to share your thoughts on the use of advanced composite materials for major infrastructure. Much of the nation's major infrastructure is nearing or is past the end of its design lifespan. The American Society of Civil Engineers 2017 Infrastructure Report Card gave our nation's infrastructure a grade of D+, based on assessments of capacity, condition, resilience, innovation, and other criteria. And our current infrastructure is under increased strain year after year as our population grows. We must find a way to ensure the safety of our nation's expanding population as demands on our roads, bridges, utilities, and other essential infrastructure increase. I sit on the House Transportation Infrastructure Committee, and I understand that the status quo is clearly not acceptable. In addition, we need to examine our approach to rebuilding infrastructure as climate change and other factors drive increases in the intensity of wildfires, hurricanes, and other extreme events, wreaking havoc on dams, bridges, above and below ground utilities, and other essential structures. These are long-term challenges that require long-term solutions. But right now, we don't have the funding necessary to close investment gaps and build the infrastructure we know that we need. As we make plans to shore up our infrastructure and build for the future, we must take advantage of all the tools at our disposal. This includes using innovative technologies and emerging materials where they offer the best value for a project. Materials such as fiber-reinforced polymer composites or advanced composites, which we are examining in today's hearing, may play a key role in how the nation addresses its challenges under constrained resources. Decades of federal and private sector research and development and investment in advanced composites has resulted in a significant use of these materials in some sectors, such as defense, aerospace, automobile, and energy industries. While composites have also been used in some construction and infrastructure applications, such as strengthening concrete, making bridge repairs, and building bridge decks, they haven't been used as widely for infrastructure as they have been in other sectors. I commend NIST for producing the report we're reviewing in today's hearing. They brought together federal, private, and university partners to identify and examine how to overcome barriers to adoption of composites in sustainable infrastructure, including challenges to developing a skilled workforce. I look forward to hearing from Dr. Lange and others about ways we can incorporate advanced composites into our engineering education and training programs to make sure that all those involved in designing and building our infrastructure have the knowledge and skills to use whichever material is best for the job. This will require updates for undergraduate and graduate engineering curriculum, training programs for the construction trades, and professional development plans in a wide range of industries. Doing this successfully necessitates the cooperation of governments, educational institutions, and industry. I'm glad we have representatives from all these sectors here today. As we examine ways to increase the use of advanced composites, it is important that we don't lose sight of the strength of traditional materials like concrete and steel. Both for repair and upgrades of existing infrastructure and for new projects, we need to have safety and design standards in place that allow engineers to choose the best material for the job and allow novel and traditional materials to work together. Finding smart ways to improve our roads, bridges, pipelines, and other infrastructure is a major priority of mine. I look forward to your testimony today. I thank you, and I yield back.
Hey, all right, now I'll introduce the witnesses for today. First of all, Dr. Joannie Chin. Our first witness today is the Deputy Director of Engineering Laboratory at NIST and one of the 7 research labs within NIST. As Deputy Director, Dr. Chin provides programmatic and operational guidance for the engineering lab and includes nearly 500 federal employees and guest researchers from industry, universities, and research institutes. It is the engineering lab's mission to promote the development and dissemination of advanced manufacturing and construction technology guidelines and services to the U.S. manufacturing and construction industry. Prior to being Deputy Director, Dr. Chin previously served as the leader of the Polymetric Materials Group. Dr. Chin received a Bachelor of Science in Polymer Science and Engineering from Case Western Reserve University. She received a Master's of Science in Chemistry as well as a PhD in Materials Engineering Science and from Virginia Polytech Institute and State University. Our second witness is Dr. Hota GangaRao. Wadsworth Distinguished Professor and in the Statler College of Engineering at West Virginia University. He also serves as a Director of Constructed Facilities Center and Director of the National Science Foundation's Industry University Cooperative Research Center for Composite Infrastructure at West Virginia University. Dr. GangaRao specializes in fiber-reinforced polymer composites, bridge structures, advanced materials research, composites for blast and fire resistance, and others. Dr. GangaRao received his PhD in civil engineering from North Carolina State University and is a registered professional engineer. And Mr. Lipinski, you want to introduce Dr. Lange?
Thank you. It's my pleasure to introduce Dr. David Lange, Professor of Civil Environmental Engineering and Director of the Center of Excellence for Airport Technology at the University of Illinois at Urbana-Champaign. Dr. Lange also serves as President of the American Concrete Institute, a technical society and standards developing organization. Dr. Lange holds a BS in Civil Engineering from Valparaiso University, an MBA from Wichita State University, and a PhD in Civil Engineering from my alma mater, Northwestern University. I almost majored in civil engineering, but I went with mechanical there as an undergrad. So Dr. Lange's been a member of the faculty at the University of Illinois for the past 25 years and has earned numerous awards and honors, including the prestigious NSF Career Award, a Fulbright Award, and several accolades for his publications and teaching. Dr. Lange's research focuses on an interface between the structural engineering and materials science of concrete and includes topics such as airport pavement, recycled concrete, and fiber reinforcement of concrete. His research group has played an important role in the O'Hare Airport Modernization Program, coming up with design concepts that have saved the Chicago Department of Aviation millions of dollars. I also understand that when he's not in the lab, Dr. Lange enjoys spending time with his 5-month-old granddaughter and is looking forward to another granddaughter on the way. And congratulations. And I want to thank you for being with us today, Dr. Lange, and I look forward to your testimony.
Our final witness today is Mr. Shane Weyant, President and CEO of Creative Pultrusions Incorporated, located in Alumbank, Pennsylvania. Creative Pultrusions is a subsidiary of Hill and Smith Holdings, PLC, an international group with leading positions in the design, manufacture, and supply of infrastructure products and galvanizing services. Creative Pultrusions is a leader in the manufacture of fiberglass reinforced polymer pultrusion products. Mr. Weyant has been in the Creative Pultrusions for nearly 30 years. He received a Bachelor of Science in Economics from Frostburg State University, where he graduated magna cum laude. And now, Dr. Chin, you have 5 minutes to present your testimony.
Chairman Webster, Ranking Member Lipinski, and members of the subcommittee, thank you for this opportunity to discuss NIST's role in promoting the adoption of advanced composites to renew our infrastructure and to increase its resilience in communities prone to or recovering from disasters. At NIST, our world-class experts use unique facilities to measure materials with increasing precision and characterize new materials for the first time. We help American industries develop, test, and manufacture products with features that outperform previous generations. Our broad program in advanced materials includes advanced composites, that is, polymers reinforced with fibers or other additives. Advanced composites can play a significant role in renewing our nation's crumbling infrastructure and help existing infrastructure be more resilient to both usual wear and natural disasters. Compared to traditional materials, advanced composites are often stronger, lighter, and longer lasting, thereby offering many cost savings, including fewer days lost to repair and maintenance. That means fewer hours stuck in traffic, detoured around bridges, roads, and levees under repair, fewer days in the dark due to broken utility poles, and more efficient movement of the goods and services that underpin our economy and quality of life. The American advanced composites industry contributes about $22 billion to the economy each year. And although we currently lead the world in advanced composite technology, adoption of these materials for infrastructure has been slower in the US than in Canada and Europe. To understand the barriers to using these materials in the US, NIST convened a workshop in February 2017 with infrastructure engineers, designers, and owners in partnership with the American Composites Manufacturers Association. This May, we will hold a similar workshop with stakeholders interested in using advanced composites to reinforce existing structures to make them more resilient to seismic events. So from the NIST ACMA workshop, we learned that many owners and design professionals don't yet have enough confidence in the reliability and long-term durability of advanced composites to specify their use in new structures, as well as to repair damaged ones. We also learned that designers and engineers need data and design guidance so they can provide appropriate safety margins while maximizing the weight and cost savings of these materials. NIST has the expertise to address these needs. We have been studying advanced composites since the 1980s and are a leader in characterizing the performance and properties of advanced composites on all scales, from nano to macro. For example, to study durability, we have developed sensors that visualize the molecular nature of damage in composites. We also have a unique device that accelerates the effects of weathering on materials and large-scale testing facilities that evaluate the effects of strong loads on advanced composite structures. Our experience providing a data infrastructure for the Materials Genome Initiative is now helping members of the advanced composites community capture and share information on material properties. We will assist the advanced composites community as they establish a clearinghouse of curated existing design guides and data from completed projects, which will inform additional science-based codes and standards. Our Community Resilience Program provides guidance to architects, design engineers, and community leaders to enable critical decisions about which materials help communities recover rapidly and build back better. While NIST is not a regulatory agency, we have long provided strong scientific foundations for the consensus standards developed by industry. NIST staff members provide leadership and technical expertise through more than 1,800 positions on committees for ASTM International, the International Organization for Standardization, and other standards development organizations. So we greatly appreciate the members of this committee and others in Congress for their support of federal acceleration of the adoption of advanced composites for infrastructure, helping to keep our nation globally competitive and economically secure, and contributing to our quality of life. I am happy to answer any questions you may have.
I recognize Dr. GangaRao for his 5 minutes.
Honorable Congressman, Chairman Webster, members of Research and Technology Committee, I'm immensely grateful for your invitation to speak on my theme today, which is the infrastructure renovation through smart composites manufacturing and construction, coupled with testing standards and enforcement. As all of you know in this room, our aging, perhaps aged infrastructure is rapidly deteriorating, certainly not collapsing. Bulk of our infrastructure problems can be attributed to $1.5 trillion funding gap between the revenue and the infrastructure needs for 2016 to 2025. This is costing $3,400 per year per family and leading to 2.5 million fewer jobs, and even more importantly, $7 trillion loss to businesses. How to bridge this need versus revenue gap? The above, do we need more debt? Do we need to increase the gas tax? A couple of these above will have adverse effects on our economy, as you all know. Today, I want to present an alternative to this august body that is about, instead of replacing crumbling infrastructure, as our Congressman Lipinski pointed out, we should provide resources to renovate our infrastructure to get the biggest bang for the buck using advanced composite materials. Currently, composites account for less than 1% of the structural materials by volume, in spite of their many advantages, such as the high strength, corrosion resistant, lighter weight, and better performance per unit weight. What are the challenges ahead, and what are the economic advantages? Producers of steel and concrete should not view composites as a competitive product or as a threat to their markets. Composites will never fully replace traditional materials, but they are another tool in a toolbox, and they would be hybridized well with steel and concrete. Through our National Science Foundation funded center entitled Center for Integration of Composites into Infrastructure, we have shown composite wraps have been used to renovate several deteriorated structures at 5 to 10% of the replacement costs, or by repairing some of the concrete piers, steel piles, and the list goes on. At West Virginia University, we worked on lighter bridge decks, weighing only about 1/4 of a typical concrete deck. We worked on sheet piles with our industry folks to protect coastal erosions using composites. We developed utility poles that cost half the cost of steel transmission towers. And we also are developing high-pressure gas pipes to push more gas at a faster rate. We involved heavily in navigational structures such as the lock gates, and the list goes on. Efforts are underway to develop composite modular housing subsystems that are multifunctional, model, mold-free, and durable. Using smart manufacturing and construction methods, housing costs can come down dramatically, as it has been done by Henry Ford's assembly line type operations. To be at the cutting edge of research, development, and innovation of composites in infrastructure, NIST workshop, as alluded now a few minutes ago, of 2017, identified 5 critical areas to be overcome. One of them we can do here is to help the industry develop smart manufacturing and construction tools with composites, and also develop uniform codes and product qualification through third-party certification. Need to require future projects to consider composites as alternate designs. We need to invest in 3.2 million workers dealing with the designs, contracts, maintenance, and management of composites. In conclusion, composites are cost-effective and durable. Large-scale applications of composites will create huge markets and open new opportunities, including the smart rehab methods and educating 3.2 million American workers dealing with the construction-related industry. To enhance American productivity of workers, we must invest in the composites in terms of research, development, and implementation. Finally, to maintain public safety, investment in infrastructure restoration through composites and hybridization with conventional construction materials have to be made in tandem with standardization of products and quality control. Thank you very much.
Dr. Lange, you're recognized for 5 minutes.
Chairman Smith, Ranking Member Lipinski, and other committee members, I appreciate this kind introduction and opportunity to share my ideas today. I wear 2 hats today, one as Professor of Civil Engineering at the University of Illinois, the second as President of the American Concrete Institute, an organization of 20,000 members from the construction industry, the design profession, and academia. FRP is a class of high-strength, low-weight, and durable materials that can be fabricated in a wide array of shapes and properties. The attractive aspects of FRP have motivated significant investment in research and many funded demonstration projects over the years. Despite attractive attributes and a successful track record in field demos, we do not see a widespread adoption of FRP in construction today. Certainly one explanation is the presence of 2 dominant design paradigms in commercial construction: reinforced concrete and structural steel. These tried and true systems have a 100-year head start on FRP. Furthermore, concrete and steel technologies are not standing still. Large organizations like the American Concrete Institute work tirelessly to advance these technologies. A century of commitment at ACI assures that today's concrete is not your father's concrete. The adoption of FRP depends on a wider effort to harmonize material systems. The 2 dominant silos, concrete and steel, need effective crosstalk and openness to new materials such as FRP. It can be done. As an example, ACI has opened a path for use of FRP rebar, and ASTM has released specification language for those bars. Market penetration of FRP should be driven by authentic advantages: durability, low weight, organic shapes, flexibility, high strain capacity. Those are among the competitive advantages of FRP. Indeed, FRP has excelled in certain applications. The aircraft and marine industries, and more recently, the market for wind turbine blades and cooling towers have embraced FRP. In construction, FRP products have found a place in market niches such as corrosion-proof rebar and as a material for repair of concrete structures. Despite seemingly high potential for FRP in infrastructure, the topic is almost non-existent in civil engineering education. Courses dedicated to FRP and structural repair are rare among the 220 civil engineering programs in the United States. Engineering education has not functioned as a change agent. There are opportunities to affect civil engineering education. Like other professions, civil engineering is moving toward requiring more than a bachelor's degree to practice in the profession. As master's degrees grow, the curriculum can better accommodate specialty topics like FRP if the need from industry were to drive it. Beyond that, we need courses that harmonize concrete, steel, masonry, wood, and FRP. The future is a world with better integration of material systems. Now, a few words about the NIST roadmap. I think the roadmap has attractive elements. In particular, I'm drawn to one of the recommendations related to the design data clearinghouse barrier. The idea is to charge NIST as a neutral party to compile durability data and define limits using codes and standards. Indeed, we can see how codes and standards can spur adoption of FRP. The 2017 release of ASTM D7957 for FRP rebar has already had impact on the ability for that product to be specified and designed. Just days ago, an industry representative shared with me his positive outlook that is based on an upswing in FRP bridge deck projects in recent months. I also endorsed the roadmap plan for its emphasis of FRP curriculum for civil engineers. Given the large body of existing research, it is reasonable that federal funding could foster a modernization movement for civil engineering curriculum that bolsters design of FRP and harmonized material systems. Lastly, I want to encourage use of a proven mechanism available to the federal government. That is, research centers that incubate partnership between academia and industry. My own experience as director of the Center of Excellence for Airport Technology has persuaded me that large infrastructure programs can benefit from sustained partnership with universities. Since 2005, SEAT has received funding from the O'Hare International Airport and the Chicago Department of Aviation. Every year, we select our research projects to inform the decision-making process, reduce risks, and save money. Our 12-year track record with O'Hare suggests this has been a successful model. Thank you.
Thank you, Dr. Lange and Mr. Weyant.
Good morning, Chairman Smith, Ranking Member Lipinski, and the members of the subcommittee. On the behalf of Creative Pultrusions and my fellow members of the American Composite Manufacturers Association, I appreciate the opportunity today to testify before you on an issue that is vital to our industry involving the essential role NIST plays in material standards. I am happy to be here to explain the value that composites offer consumers, communities, and industries across the nation. With manufacturers in each of your districts, we are a great example of made in America manufacturing, whose potential has only begun to be realized. Composites are stronger than other materials such as steel, concrete, and wood. They are lighter and more energy efficient and easier to transfer and install. They offer greater durability and, most importantly, are resistant to corrosion and structural degradation. Many of you are already familiar with fiberglass boats. Saltwater destroys traditional metal and wood hulls, but fiberglass remains unscathed after decades of service and has come to dominate that sector due to the performance. Using the same material system, we and other composite manufacturers provide infrastructural solutions with performance and other benefits that can far exceed traditional materials of construction. Let me highlight a few examples. Composite bridges that can be manufactured off-site, installed in less than 1 day with less traffic disruption, and that require minimal maintenance throughout their service life. Composite rebar that can replace steel rebar in traditional concrete construction and is resistant to rust so it won't degrade. Composite utility poles and crossarms that are easier to install, are more durable against extreme weather and fire, require less maintenance, and last significantly longer. Only 8 utility poles were left standing in the Virgin Islands this past year after the hurricanes. Those 8 poles were composite poles. Despite these benefits, barriers to deployment of composites remain. Fortunately, some of these obstacles can be cleared with the help of sensible government and industrial participation. A great first step was the 2017 workshop that brought folks from NIST together with a wide range of private and public stakeholders to work towards solutions. I felt the workshop was a great example of positive engagement between industry, academia, and government because it produced actionable results. What we know from experience is that the lack of awareness of, and importantly, standards for, composites is our threshold problem. NIST can aggregate existing standards and design data for composites and validate them for broader dissemination and use. This will help all stakeholders to see the totality of data on composites and understand the further research needed. Their world-class laboratories also can help develop durability and performance testing for composite infrastructure products. This data can support further development of standards of composites and better arm engineers with the performance knowledge to make them more comfortable with using composite. Given NIST's role in standards and research, the agency has a unique capacity to assemble a broad swath of stakeholders and ensure that this work is impactful. We believe all materials, techniques, and designs should stand on their own merit. Our experience with builders and project engineers show that there is a limited knowledge about composites as a structural material throughout the design community. Additional research and data that can contribute to standards development will help raise the knowledge about composites. Likewise, bringing together the various agencies responsible for infrastructure investment to participate in this effort can help diffuse knowledge to the asset owners and designers. An existing example of similar collaboration is what is going on with the Institute for Advanced Composite Manufacturing and Innovation. Part of the Manufacturing USA Network, IACMA, working with academia and industry and federal agencies, has developed an exciting new technology to recycle composites. Productive collaboration demonstrates that federal investment in composites pays huge dividends, and coupled with further structural research by NIST we discovered today, will help composites contribute more to the overall sustainability of our infrastructure network. The demands placed on America's infrastructure have never been greater. To build a network to support the 21st century population and economy, there needs to be greater availability of 21st century technologies. With some smart investment and hard work together, we can make bridge, water systems, and grid failures something of the past. The ability to build structures that last centuries instead of years is here. We look to Congress for support to help make this happen. Thank you.
Thank you all so much. Appreciate your testimony. Appreciate you being here. I'm going to wait with my questions and recognize the gentleman from Indiana first for 5 minutes.
Thank you, Mr. Chairman, and thanks to each of you for being here this morning. We all recognize the need to improve our nation's infrastructure, but we also recognize the precarious fiscal situation that we find ourselves in today. The CBO estimates that we are on track to run $2 trillion annual deficits by 2028. The CBO also found that we will run $82 trillion in total deficits over the next 30 years. We need to focus on reducing government spending wherever we can. So from what I understand, the main benefit to using composite materials as opposed to steel or concrete is the reduction in maintenance cost over the long term. So my first question for each of you, is there any data on what kind of cost savings can be expected over 20 or 30 years by using composite materials for various infrastructure projects? Dr. Chen?
My colleagues from the industry would have more specific figures on the actual cost savings, but we are very much aware of studies and existing installations that have demonstrated great reductions in installation costs, impact on the economy in regards to road blockages and delays, as well as maintenance and repair, as well as replacement over the lifetime of the structure.
Okay.
As I stated in my testimony, we have rehabilitated over 100 structures across the country from West Virginia University's Constructed Facilities Center. I'll give you 2 examples, and I'll shut up. One of them is there's a East Lynn Viaduct. We rehabilitated it for about 20% of the cost of replacement in Parkersburg, West Virginia. When I took that job, they said if it survives 5 years, back in 1999, they said they would be happy. Last year, we collected the data, and it looks brand new. The second example I like to quote, which I have done the rehabilitation renovation part, was for Army Corps of Engineers. Again, we were able to rehab that complex bridge system with $120,000, while in fact it would have costed $4 million to replace it. So the list goes on. I'm not going to stand here and talk about it anymore, but I'll be very happy to supply you with all the cost data and also the durability data if you need.
Your remark about the main benefit of FRP being reducing maintenance costs, I think there's truth in that FRP is a very effective repair material. We're seeing this used in sheet products that are put onto reinforced concrete structures, and it's one of the least expensive ways to add strengthening in many cases. I'm not so sure I would say that that's the main benefit of FRP, though, because I think having a landscape for design where you have multiple materials being used, a real portfolio of materials, is where we could get even more benefit in the future. I think there's been some limitation to have civil engineering organized in silos, where you have the reinforced concrete community, the structural steel community working somewhat independently, and FRP wondering how do we fit into this situation. And I think there's probably a higher calling to try to figure out how to give all materials sort of equal access. In some respects, engineers should be material agnostic. I don't really care what particular material, I want to get a result. And having all those materials available will be the best benefit of having FRP in the game.
Okay, and Mr. Weyant, before you answer that question, perhaps with the time left as well, you can answer the question of what would the cost benefits of replacing or restoring electric lines with FRP composite poles be?
On the electric line, it's more in the reliability, how they withstand a lot of the storms. We see that a lot with a lot of the electric companies. They're understanding that value now by investing in composites for that reliability. As far as the life cycle, I look at it a couple ways. Not only on the maintenance side, it's also the installation side. We have seen cooling towers, marine markets with sheet piling, and also in the utility industry, that we have seen probably 30% overall life cycle cost savings when using composites.
Thank you. My time has expired.
Gentleman from Indiana yields back. Recognize the gentleman from Illinois, the ranking member, Mr. Lipinski,
Thank you.
for 5 minutes.
I wanted to say, first of all, that as Mr. Banks was talking about the savings for government, for taxpayers, which I think is critically important. The other part that I wanted to ask about is what can we do as policymakers here in Washington to make sure that the U.S. Maintains a strong position in producing in these materials. Obviously, FRP, and when we're talking about even things as large as bridges, can be put together elsewhere and brought over to the United States to be put in place. We've seen that with concrete and steel bridges. So what can we do to try to make sure we have the right incentives in place for the U.S. to really our economy and jobs to thrive in this, with FRP. So let's start with Dr. Lange.
Well, one thing that I would like to emphasize is that we have opportunity when we have very large infrastructure programs. O'Hare just announced another $8.5 billion program that adds a terminal to the west side of O'Hare. And these kind of major infrastructure programs extend for many years. The opportunity to partner with university researchers to help answer questions about what is going on in that project and how new materials might come into it, how new technologies might benefit the project, that I think is a great opportunity. And so the relationship we've experienced in working directly with a major infrastructure program is not terribly common. It's a little bit of an unusual thing that we have that kind of a partnership. But I believe it could be a very good policy moving forward that we have these major programs pay attention to the research landscape.
Thank you. Anybody else? Dr. GangaRao?
Thank you. Thank you. I have indicated 6 different approaches of how we can keep the lead in terms of our high-quality products based on composites in my write-up, and I'll talk about a couple of them. One of them is that we do not want to be a dumping ground for some inferior product from outside. Therefore, we need to maintain very high standards and also enforce these standards of the materials that we are going to be introducing as composites, or for that matter, as a hybridized material, including the conventional materials like steel and concrete. That's one. I can elaborate on that much more later. The second important thing is we need to come up with smart manufacturing for infrastructure point of view in terms of creating as large a subsystem as possible under the manufacturing settings so that we gain certain degrees of efficiencies and be able to reduce any form of wastage that we have right now. About 40% is a waste in the construction industry. So these are the 2 I would like to focus on. I have 4 other items I mentioned in my write-up. Thank you.
Thank you. Mr. Weyant, do you have anything to add?
Yeah, I echo Dr. Lange and Dr. GangaRao's position. I think government needs to take a strong position in 2 areas. We need to invest to enhance the development of the technologies to keep us on the forefront, and the materials, to be produced in the U.S. Also, we need to rebuild America with the right materials. Why we're facing these problems of the large spend on building the infrastructure is because these materials are not lasting. We got products here that can be 50 years plus design service life. So down the road, the payback is, as I said earlier, on the life cycle. So we need to make that choice today to rebuild America the right way and put people back to work.
And Mr. Weyant, it probably may surprise you that I've driven through Pleasantville many times on my way from here to Johnstown. So I want to ask you about, you have issues with the labor force, getting workers who are capable.
That is a big demand nowadays, but we reach out a lot to a lot of the local high schools and a lot of the trade schools, very aggressive on recruiting, but, to train people too, that is a concern. And in the rural area, as you know, Mr. Lipinski, that does put a big demand because we have a lot of expansion in our areas with a lot of different manufacturers.
Thank you. Yeah, time will yield back.
Gentleman from Illinois yields back. I'll now yield myself 5 minutes. First, again, I want to thank you all for being here, for your testimony. For me, this is an especially important hearing today. The state of Illinois, as my colleague and friend from Illinois has already stated, leads in material science research conducted at our wonderful universities and national labs. I want to hear what we're doing nationally, but I always like to see how Illinois universities are testifying before this committee. I'm grateful for that. Infrastructure is also a key priority with every local official I meet with, and it's why I work to preserve key tools for municipal finance in the tax reform bill that we had, such as the tax exempt status for municipal bonds. Local officials understand the importance of both construction and maintenance, and they see the long-term impact of more resilient infrastructure. So thank you for your work. Dr. GangaRao, if I could address my first question to you, how would research at NIST be integrated into standards development and used by standards development organizations?
NIST has excellent facilities in trying to promote any kind of test methodologies, develop the test methodologies, and also enforce the testing systems. That's one way they can do it. The second way they can do it is by providing excellent platform in terms of educational aspects. There are half a dozen educational aspects that I can talk about. They can be the lead nuclei in developing some of these educational aspects. And thirdly, they have great amount of technical know-how through their full-time employees, and they can certainly interact with not only the university types, but also with the industry types to promote some of these kinds of advances in a most systematic fashion. Thank you.
Thank you. Mr. Weyant, in your testimony, you say that there is limited awareness by engineers and asset owners about the composites as a structural material for infrastructure. I wonder if you could describe in more detail what you encounter.
A lot of times when we approach the design community, when you have to introduce a composite material, a lot of the traditional materials have design codes, okay? They have their own handbooks. When you buy a steel beam from XYZ company versus ABC, you know you're getting the same steel beam. Those standards need to be developed. You know, composites being fairly new in the construction market, you know, really came about in the mid-'80s to '90s. Those standards, a lot of the engineers do not understand them. So we have to educate them, and a lot of the companies are a lot smaller and don't have those resources to really put, you know, in the technical design capabilities to help educate the engineering community.
Thanks. Dr. Chin, it's been cited in numerous reports, including one in 2014 by the President's Council of Advisors on Science and Technology, that composites are a cross-cutting enabler for the manufacturing technology of the future, supporting not only infrastructure, but also automotive, aerospace, energy, and other key sectors. I wonder if you could elaborate on the strategic importance of composites to the national economy.
In regards to the more general application of composites in the sectors that you mentioned, the considerable weight reductions through the use of composite materials enable energy savings. That's the primary driver in the aerospace, marine, and automotive industries. In infrastructure, it's not a matter of designing for based on weight constraints, but the availability of composite materials that can be prefabricated, pre-manufactured off-site, brought to the construction sites and installed much more quickly. The weight savings in this particular case also lends itself to much more rapid installation, which mitigates the delays, obstacles, roadblocks, all of the issues involved with construction projects that reroute people and goods around the points where the construction is taking place. Those have an impact that maybe is not as measurable in terms of economic return on investments, but you can definitely see the impacts on the lost time and you know, just in terms of the process of getting people and goods from point A to point B, there's definitely a dollar value associated with those benefits of composites as well.
Thank you. I'm just about out of time. I may follow up if that's all right with you. I had another question just in regards to opportunities for students and graduates to obtain hands-on experience with composites, with internships and research. So I may follow up to see if I can see if you have suggestions or ideas from that. With that, my time is expired, and I would recognize the ranking member of the full committee, Ms. Johnson from Texas, for 5 minutes.
Thank you very much, Mr. Chairman, and Ranking Member Lipinski for holding this hearing. and thanks to all the witnesses for being here. In addition to this committee, I serve as a senior member of Transportation and Infrastructure, and I really do understand the challenges that we face in crumbling infrastructure. My home district of Dallas, Texas, was recently named the fastest growing metropolitan area in the country by the U.S. Census, but it also rated as the 10th worst city in the nation for traffic congestion in another recent report. And though there has been great improvement from last year's position, which was number 5, commuters still face a daily tackle with bottlenecks, wasting time and fuel, and this is a struggle for many communities, I'm sure. And while it is an example of perhaps reaching the stars, I'd like you to explain to me what your feelings are about what type of emerging technologies that we will be looking at for our infrastructure needs, and also how would we go about preparing our workforce. I'm particularly interested in the emphasis on resilience in materials that we use and the talent that's needed. We're already looking at aerial transportation, drones, and all kind of alternative things. What seems to be realistic? And I'd like to hear from each of you.
Well, let me chime in with one idea here. One thing that I would like to kind of add about this discussion about durability is that if you want durable infrastructure, you need to ask for durable infrastructure. And kind of an old saying, you get what you ask for. And too often our contracting mechanism is based on low bid, that people are asked to, say, build a road or build some infrastructure, and the winner of that competition is the one who prices it the lowest. And when you look to the specifications, they don't emphasize durability like they should. They don't emphasize life cycle as they should. The choice is made on initial cost rather than on life cycle cost, where you take into account the full length of the structure and its maintenance costs. So one issue that is a policy issue is how can we move more toward performance specification and looking at life cycle cost.
Thank you. Yes.
I'd like to start out by stating certain issues with regards to resilient infrastructure. With my center, that is the NSF-sponsored one, dealing with the composites for infrastructure, University of Texas at Arlington is a member of our center, and they have been using composites to try to minimize your expansive shale problems for your foundations and the roads. So there again, we need to use some of these advanced materials that would help enhance the service life of each and every one of these infrastructures. That's just one of the many other parts. The other part is we need to marry these advanced materials with the conventional materials so that the longevity can be improved, the traffic jams can be cut down, and what have you. And there are many other transportation systems, including some of the electronics that are going to be built into it, coming into vogue, that will greatly enhance the efficiency of movement from point A to point B. Thank you.
Thank you very much. Anybody else?
So one of the big national multi-agency programs that NIST is involved with is the Materials Genome Initiative. And through that program, the development of innovative materials is we seek to accelerate the development of these innovative materials that can be used in infrastructure as well as many other industry sectors. But this type of program would enable material scientists and engineers and designers to be able to receive the benefits of materials developed at a much faster rate, which could potentially be used in infrastructure and making it more resilient to natural disasters and other types of high impacts. We also have a community resilience program, which seeks also to develop more infrastructure, more resilient materials for use in infrastructure.
Thank you. My time's expired. But
Gentlewoman from Texas yields back. The gentlewoman from Connecticut, Congresswoman Esty, is recognized for 5 minutes.
Thank you very much. And again, I want to thank the chairman and ranking member for holding today's hearing. You will find, I think all of us are on the Transportation Committee, and there's a reason that we're also on this committee, because we recognize the important challenges facing the country on resiliency and our infrastructure, the aging infrastructure laid out so well by you. I've also been working on this, and I will make sure to get copies of this for each of you. There's a bipartisan group of Democrats and Republicans in the House called the Problem Solvers Caucus, and I was the co-chair of this report, which we released in January, making several of the points that you underscored. Dr. Lange, you just recently talked about the importance of life cycle costs. We specifically calling for that. My father and grandfather were both civil engineers. I know exactly what you're talking about, and it is the low bid problem. That's always been a problem, but never more acute than now, when we really need to be looking at the entire cycle of the costs, better from day one and lasting much longer. I'm also co-chair of and co-founder of the Corrosion Caucus. So we've been looking at these issues in the Resiliency Caucus, the importance of upgrading those requirements. So I wanted to also flag again, so you know that a number of us have been working on this in multiple committees. We've called for the creation, in the report we called for the creation of something like an ARPA H2O to look at the water infrastructure, which is often not included in the civil engineer's report, because that alone is, approaching $1 trillion of unmet needs to replace and upgrade the nation's water infrastructure. So when I get to questions, I'd ask for your thoughts of whether you think something like an ARPA H2O makes sense for basic research, especially given that water is delivered at the local level and cannot possibly have the research facilities to figure out if you're Detroit and you need to reduce the size of your mains by 3/4 to keep the flows in place. They can't be paying for that research. It's just not reasonable. We need to have a federal role in that. Chairwoman Comstock and I, who chairs this subcommittee, are getting ready to introduce a bill in the coming weeks on this basic issue of composites, on the importance of highlighting the need to include this as innovation and to include this with new standards. One of the pieces we've looked at and are calling for, and it's the Imagine Act, the Innovative Materials in American Grid and Infrastructure newly expanded. You can tell that was put together to make out Imagine. But the Imagine Act calls for the creation of an interagency innovative materials task force to assist in some of these issues we've talked about this morning, for assessing existing standards and test methods and then compare them against these new materials and how they compare. The interagency task force would work to identify key barriers in the current standards that inhibit market adaptation and adoption, and develop new methods of protocols as necessary to encourage incorporations. This interagency task force would be chaired by NIST, by the National Institute of Standards and Technology, bringing together the Federal Highway Administration, the Army Corps of Engineers, and EPA, and other standard regulatory agencies. So, Dr. Chin, can you comment on whether you think that would be helpful to have a coordinated effort across the agencies, which otherwise are siloed, as we know, which is a huge problem? Thank you.
Yes, NIST has had a very long history of collaborating with other federal agencies and other primary stakeholders in big national initiatives, such as the one that you're describing. We are absolutely committed to working in the area of water. That is definitely seen as an area of great importance to the nation.
And what's your thoughts on something, or any of you want something on the basic R&D side? Something like an ARPA H2O, is that, do we think we're at a point that there should be basic research, or is it more a function of standards and dissemination of best practices?
Well, I think on the subject of basic research, you're touching on one of the biggest challenges that we have, and that is the durability, interaction of materials with their environment. Dr. Chin talked about how NIST has a long history of looking at durability issues. I think that the durability topics are more challenging and more necessary than, say, looking at mechanical properties of materials. And so I would encourage that kind of direction of looking at durability first.
Thank you. Go ahead.
Basic research is always extremely important, no question about it. However, to get the biggest bang for your buck, good bit amount of monies have to be invested in field implementations, experimentation, and evaluations as soon as possible so that we establish a protocol of how to do some of these in the field and able to disseminate this knowledge base in a wide-scale manner. Thank you.
Thank you very much. And I'm saying I'm out of time. Thank you.
Thank you, gentlewoman from Connecticut yields back. The gentlewoman from Oregon, Ms. Bonamici, Congresswoman Bonamici is recognized for 5 minutes.
Thank you very much, Chairman Haltgren and Ranking Member Lipinski, and thank you to all of our witnesses for being here today. I'm very glad that we're discussing infrastructure and listening to my colleague talk about things like the corrosion caucus. You know that we're all interested in this issue. We know that making long-term investments in our nation's infrastructure stimulates the economy, creates jobs, and drives commerce. And as we restore our roads and bridges and build affordable housing and invest in public transit and upgrade our schools and ports and water systems, we need to be responsive to environmental concerns, but also creative in the use of emerging materials. And I am the co-chair of the Oceans Caucus, and marine debris is one of our priorities. And recently I've been reading about projects that integrate plastic bottles and materials salvaged from debris in the ocean into asphalt to create more durable roads. And this is the kind of ingenuity we need as we develop an infrastructure proposal. And I know the chairman of the full committee is gone, but I know that Texas is working on a pilot project on this as well. At Oregon State University in my home state, the Hewitt Materials Performance Lab has been one of the leaders in innovative efforts to test composite materials. The lab is conducting sensitive electrochemical investigations to study both corrosion phenomena in metals and alloys and the performance and durability of coatings and composite materials. And I visited there, and they're doing some great work. Dr. Lange, I wanted to ask you how federally funded researchers at universities can best partner with engineers in the private sector to support continued advanced research, testing, and standards development.
Okay, well, I would say that one of the themes that I have hit on, this idea of partnering with major infrastructure programs, is something I would put back on the table. I think that when you're spending, as O'Hare is going to spend $8 billion on the next phase of expansion of the airport, there should be a piece of that used for looking toward the state of the art. And engineers on everyday tasks may not have time to see that state of the art very clearly, but in partnership with universities, perhaps they can. With respect to recycled materials, I think that's a great theme to continue to hit. One thing I would encourage is that as you think about recycling materials, try to have some integrity to what you're trying to do with these materials, because sometimes concrete and other uses of recycled materials are almost using concrete as a trash can. How many things can we throw into concrete or asphalt, and we don't care that much about the degradation of properties that happens when we do it. So we really want to find synergy where we get not only use of the recycled material, but improvement of properties, not a degradation of properties.
Absolutely. Well, I'm from Oregon. We recycle everything. So, so in Northwest Oregon is not a question of if, but when a tsunami triggered by an earthquake happens. We have the Cascadia subduction zone is going to hit our state. We are overdue. So we've been having many conversations about rebuilding our infrastructure to withstand these natural disasters. And in the district I represent, the Newburgh-Dundee bypass has just been built to withstand a 9.0 earthquake. But an earthquake is not the only threat facing our nation's infrastructure. We also need to be resilient to the effects of climate change. And of course, with the ocean, we're seeing acidification, we're seeing more extreme weather events. What is the current state of our understanding of how climate change affects infrastructure, and how has that understanding shaped the composites research agenda and standards development to make sure that resiliency is a factor in anybody who wants to weigh in on that.
I want to answer a couple of things along those lines. Before I do that, I want to talk a little bit about the recycling aspect of it. At West Virginia University, we have been doing a lot of recycling of composites. For example, we can talk in terms of low-grade material recycling as well as the very high-grade material recycling. And we have done polymers to recycle and create core material that are of low value, while in fact create a very high-grade material as a shell for a given system. And that helped a great deal. And also, we are partnering now with Mexico, CONISAT, which is the equivalent of NSF of ours, where they want to recycle a lot of their high-end composites coming out of aerospace and other places. There are 3 or 4 different ways of recycling it. One is just simply burn it. That's not the best approach. There are a few other chemical ways of recycling, and we are looking at those kinds of things as well to enhance our productivity levels in the area of composites, as opposed to dumping in the oceans like you are referring to.
Right, right. Thank you. And just, I know I'm out of time, but with the chairman's indulgence, would you address the climate change issue?
I don't know a whole lot about the climate changes. As Dr. Chen pointed out, I think the amount of energy required to produce a unit pound of a composite per unit workability and the efficiency of a composite is much less than steel or concrete.
Thank you. I yield back, Mr. Chairman. Thank you.
Thank you, the gentlewoman from Oregon yields back. I want to thank all of our witnesses for your testimony and all the members for their questions today. I also do want to send regards from Chairwoman Comstock, who really wanted to be here but was not feeling well today. So she sends her regards and gratitude for each of you being here. The record will remain open for 2 weeks for additional written comments and written questions from members. With that, the hearing is adjourned. Thank you so much.
Thank you very much.